Hello, algebra students. So today's notes are on the distributive property, and this should be a little bit of a review. Hopefully the distributive property is familiar to you, but the idea here is that if you have A times the quantity of B plus C, then that is equivalent to A times B plus A times C. And typically you see this represented by drawing little arrows. So if you have a number or a variable or term on the outside of parentheses like this A, we can multiply it in to each term on the inside. So I can do A times B, and that gives me the term AB on the right. And then I could also do A times C, and that would give me AC, the second term on the right hand side. And that's the basic idea of the distributive property. So just to look at one quick example, if I have 3 parentheses 7x plus y, I would apply the distributive property by multiplying 3 times 7x, and that would give me 3 times 7 is 21, and then I still have an x. And then I would do the exact same thing with the second term to do 3 times y, and I would get 3y. So my final answer is 21x plus 3y. So at this point in the video, I'd like you to press pause and try out the U-try problem below. 5 times 2x plus 8y. What would that equal? Alright, so now we're going to look at a little bit of a different example, which is the distributive property in reverse. So this might be a little bit new, but the idea is we're starting with kind of like what is usually the end point and thinking, what did we multiply in to each of the terms if we have x plus xbc? Well, what I notice right away is that there's an x in the first term, and there's also an x in the second term. So if I was rewriting this by applying the distributive property, it's telling me that that x is what I'm writing on the outside because it's in both terms. And we can kind of imagine it getting multiplied back in what would have to be in the 2 remaining blank spots inside the parentheses. So for example, if I see on the left-hand side I have an x in that first spot, that means I would have to multiply this x outside times a 1, because we can imagine 1 times x gives me my x on the left-hand side of the equation. Now, what would I have to write in this last blank would be BC, right? Because x times BC would give me back the xBC on the left-hand side. So now, again, I'd like you to pause the video and give these U-try examples your best shot. I know this is something new, but the idea is you're trying to figure out what variable or number needs to go in the blank on the outside of the parentheses, and then what does it get multiplied into on the inside of the parentheses. Okay, so the next part of the notes, I'm going to introduce this idea of an area model to you. So the idea of an area model is that if we have a rectangle with a length and a width, then how would we find the area? Well, we know that area is length times width. Okay, so area of a rectangle is multiplication. And this allows us to represent any multiplication problem as a rectangle, which is actually really useful to organize terms when it comes to expressions with variables and numbers. So the first one we'll look at is just the basic form of the distributive property, which says A times B plus C. Now you'll notice this is in fact a multiplication problem. I have whatever A is, some number, times B plus C, which could be some other number. So we can think of this as a length times a width. Now if I was going to represent this as a rectangle, I could kind of imagine a length of, say, A, and then I'm kind of drawing out the width of my rectangle, and the width is B plus C. So I'm going to divide it into 2 pieces and say, like, this first chunk is a length of B, and the second chunk is a length of C. Now, if I think about multiplying within or finding the area of these individual rectangles, I can first look at the rectangle on the left, which is a length of A and a width of B, and say the area there would be BC, or B times C. And then in the second rectangle, it still has a length of A, and now it has a width of C, so I could say that has an area of A times C, or AC. So what this means is that the total area is the sum of those two smaller areas. So it would be BC plus AC. And if we think about the distributive property, that is confirming the distributive property. I just realized I made a mistake. Where I wrote BC, I should have written BA, my fault. And same over here, so this should be BA or AB. Sorry about that confusion, but just to kind of summarize things, if we think about the original distributive property from the beginning, we did A times B, and we got AB, and notice like that's the same thing as this BA. And then you do A times C, and that is AC. Oh, sorry, this should be a plus sign here. And this AC is the same we see here. So the area model is in line with the distributive property, but it allows us to kind of be more systematic, especially when we get to problems that have more terms than just one or two. So let's look at an example that's a little bit more complicated. So the next example is A plus B plus 1 times B plus 1. So again, I have a length and a width here. So I'm going to represent it with a rectangle. And along one side, I'm going to put my A plus B plus 1. And I'm going to do that along the top. So I'm going to divide, because there's three terms here, the A, the B, and the 1, I'm going to divide this into 3 columns. And the idea is that we have a length of A across the top, then a length of B, then a length of 1, and if we add those all together, we get our A plus B plus 1. Now along the side, I'm going to do B and 1 and divide it up. So say this is like a width of B and then a width of 1. Now I have 6 individual rectangles, which I can think about what is the area of each of those, and then I can add it all up to get a final answer. So in the first rectangle, I have A times B, which is AB. Then moving to the right, I'm going to get B times B, which is B squared, B to the second power. Then 1 times B, which is B. In my second row, doing 1 times A, 1 times B, B, and 1 times 1, 1. So now when I go to add everything up, I'm just going to kind of go across. I have AB plus B squared plus B plus A plus B plus 1. Now I'm just going to quickly look and see, do I have any like terms that I can combine within this? So I'm looking for the same variables and the same exponents. And I see I have a B term and then I have another B term. But those are the only 2 terms that are like terms. There's nothing else that has the exact same variables and the exact same exponents. So that's all I can combine, but when I do that, I get AB plus B squared plus 2B plus A plus 1. And that would be my final solution after I rewrite the original multiplication problem using the distributive property. Now, I have one more example to think about, and we're not actually going to multiply this, but we are going to think about how we could represent it using an area model. So we have A plus B times C plus D times E plus F plus G. Okay, so now if we think about length times width, we could imagine, okay, I have a length of A plus B and a width of C plus D, but then I have this whole other thing I'm multiplying, this E plus F plus G. So instead of using an area model here, we're actually going to think about volume. Because you may know that volume is length times width times a third dimension, which you can think of as depth or height. And if we think about it visually, we can kind of imagine like a cube or some sort of rectangular prism where you have a length, a width, and then a depth. So this last E plus F plus G, this last thing we're multiplying, we're going to call that the depth. Now, if we think about how we're going to represent this using the area model, so I'm going to start by just doing length times width. So I'm going to draw, and I'm going to leave some space above it, but I'm going to draw a rectangle with my length and my width. So if my length, I'll put A and B and divide it up in half to those two spaces. And then I have along the bottom, I'm going to do C and D and divide it up. And now to represent the E plus F plus G, I'm going to create the third dimension of my prism and kind of draw these parallel lines going back, which will create like a rectangular prism. And now I'm going to divide the depth into three sections, one for E, one for F, one for G. And I have to do it along the side and then along the top. And kind of carry all those lines back. So then this would be my E, my F, and my G. And then we can imagine multiplying in to get the volume of each of the individual cubes that makes up this entire shape. But we're not actually going to do that multiplication right now. I just wanted you to kind of get an idea of how we might represent it. So the last thing I'd like you to do with these notes is to write down these last two multiplication problems, and you're going to use an area model to represent the expression and then multiply. So you're going to create the rectangle, write in the terms, and then multiply together to get a final answer. We will be going over this in class tomorrow, so feel free to ask questions about anything you are confused on.